Okay, so hello everyone. Today I'm going to talk about build system of CRuby. So as you know, CRuby has its own long history, and its build system has evolved over many years. So let me share its current state and challenges and potential future directions. So let me briefly introduce myself. I'm Yuta Saito. Fortunately, I successfully completed my master degree. So now I'm no longer a student. So currently, I'm working at GoodNotes as a software engineer, and I'm working on making Swift language available on web. And so I'm also a committer to CRuby and Swift and working on WebAssembly support for both languages. So as a hobby, I'm working on Ruby.wasm stuff. So today I will start with introduction to how CRuby is built, then walk through the current build process in detail. After that, I will discuss the challenges we face today. And finally, I will share my vision and for the future. So let's start why I am talking about the build system. So my interest in the CRuby build system started when I was working on Ruby.wasm. So while porting CRuby to WebAssembly, I encountered many challenges in the build system, and the experience made me thinking that the current build system has many improvement space to make it more maintainable and efficient. So I believe that addressing these challenges, we can make the build process better for everyone in the Ruby community. So I am motivated in this. So when you want to install Ruby, how do you usually do it? So you probably use one of these version managers, so they make it easy to install version on your machine. But have you ever wondered what these tools actually do under the hood? So let's look at the fundamental build process they all use. So this is a basic build process that all version managers wrap around. So it's quite straightforward. Download a table from rubylang.org, then run configure and make. That's it. So the configure script checks your system and generates the necessary build files. Then make build the interpreter and extensions. And finally make install puts everything in the right place. So on Windows, the process is slightly different using configure but and make instead. But so while most users will build from tables, there's another way to build Ruby directly from the Git source. So this is what you will do when working on the CRuby development. So the process looks very similar, but there are several important differences between from table. So first, you need to have Ruby installed. So on your machine, you need to have Ruby installed. So we call this base Ruby. So second, you need to run autogen to generate the configure script because it's not tracked in the Git repository. So what's the difference between building from table and Git source? Well, while the build command looks pretty similar, there is actually a crucial difference in how we handle code generation. So the table must must be completely self-contained, and it cannot depend on having Ruby installed. So this is because of what we call bootstrap problem. So how do you build Ruby when you don't have Ruby? So to solve this, we pre-generate all the files that would normally require Ruby to generate, and also include them in the table. So these files include things like generated C files for parser, precompiled RB Inc, and so on. So we have seen how Ruby is built today. It might seem straightforward. So just configure and make. So that's it. But how complex is it really? So, so let's measure various aspects of the Ruby build system to understand the current state. So to understand the build process, we need to analyze the build process in detail. So I made a tool called TraceMake that helps us understand what's happening during the build. So it works by replacing the default GNU make shell with our custom shell. And it records the detailed timing information, and this gives us a trace of every command executed during the build. And we can visualize it using Chrome Trace Viewer. So this is a trace of a single build process. So the build process can be divided into three main phases: configure, make, and install. The configure phase is a single long-running shell script that checks your system features. And looking at the make phase, we can see a lot of parallel comparison tasks. I run this build on a 16-core machine, and this is running many times simultaneously. So, and finally, the install phase copies the build files to the final location. So, so now we have a way to analyze the build trace. So, but let's look at how build times have been changed across Ruby versions. So for this analysis, I used the All Ruby project created by AKR. This project is really helpful because it provides consistent way to build different Ruby versions, and it includes all necessary patches and build scripts to make older versions buildable on modern machine. So I modified a bit to collect more information, but it's working pretty well. So looking at the configure time across Ruby versions, we can see a clear upwards trend. And this is mainly because we have been adding more and more feature detection check over time. And for example, when we need to check for new system features, library, and compiler capability, whenever we add a new platform support or start using a new feature. And each of these checks is done sequentially, which explains why the configure phase is taking longer and longer linearly. So here's another interesting data point. This graph shows the number of lines in the configure AC over time. So it's approaching 6,000 lines now. And what's interesting is that this growth trend looks very similar to the configure time graph we just saw. So this correlation makes sense because more feature detection code in configure.ac directory leads to more checks being run during the configure time. So yeah, this is one of the reasons why we need to think about better way to handle feature detection. By the way, do you know who is the most active committer of configure.ac? Do you know? Any guess? Yes, you know. So clearly, Nob has made significantly more commits than anyone else. So about 5 times more than the second most active committer. So this shows Nob's incredible dedication to maintaining the build system. But yeah, so it also highlights a potential issue. We are heavily dependent on a single person for this critical part of our infrastructure. So this is another reason why we should think making more maintainable. And also, let's see the make. The make phase also shows a natural growth trend. As we add more components and feature, compression time increase accordingly. But back in the early days, Ruby took less than 10 seconds to build. Can you believe that? So now with Ruby 3.3 and later, we are looking at over 5 minutes. But note that this build was done with J1 because early version of Ruby build script cannot handle parallel compression well. So to be fair, I used J1. So it's taking longer than what you see in your machine. So now let's dive into how the build process actually works. So this is quite complex, so I will break down step by step. So let's start with make. So you might think we just use GNU make, but actually we support multiple make implementations. GNU make is the main one, of course, but yes, here is tricky part. We need to support really wide range of versions, and the latest GNU make is 4.4, but Mac OS still ships with version 3.81 by default, so we have to support that too. And also, that's not all. We also support BSD make and NMake for Windows. Supporting all these different versions and implementations really complicate our build system. But as a fun fact, my very first commit to CRuby was about fixing a build issue with old version of GNU make, so it's fun. So let's trace the build process step by step. So configure step is where things start getting interesting. So on Unix-like systems, we use auto tools, which generate the configure script from configure.ac. On Windows, we have completely separate configure.bat. The configure step generates several important files, including make file and config.h. Note that we generate make file, GNU make file, and uncommon.mk at this step. And we have interesting, in other words, tricky approach to handle different make implementations. So we have common MK file in our source tree, and that contains rules that work with any make syntax. And for other make implementation other than nmake, we pre-process this file to generate uncommon mk while stripping out nmake specific features. So let's look at how make files are organized for GNU make. So here we have both GNU make file and make file, but GNU make prefer GNU make file as the root make file. So the root GNU make file includes several other make files, the base make file, which is shared with other non-nmake makes, and uncommon mk, which we saw earlier, and GNU make, gmake.mk, which is actually, we usually put GNU make specific definitions, and yzit make is also included through this include chain. And for Windows with nmake, we have different include structure. The make file here is make file. The root make file here is make file, and it includes win32 makefile.sub, which then includes setup.mk. And also it includes common.mk as is without any pre-processing. And we still have the other case. So for other make implementations, like BSD make, we take another approach. So the configure script just concatenates the common make and yzit make file and the base make file without include. So yeah, so we have 3 different include patterns for different make implementations. So yeah, so then let's go through the actual make step. So this is what actually happens when you run make. So first we compile the interpreter core, all those C files you see on the left. Then we build mini Ruby, which is a minimal version of Ruby that can run very basic Ruby code. After that, we use mini Ruby to configure and compile extension libraries. And finally, link everything together into the final Ruby binary. So compiling C file is straightforward, so nothing special here. But you might notice that I mentioned mini Ruby here. That actually another tricky part of the process. So yes, we actually use several different Ruby variations during the build process. So each one serves a specific purpose. So we start with base Ruby, which is Ruby already installed on your system. And then we build mini Ruby, which is minimal version of Ruby, but cannot use extension library. And yeah, so there are still other Rubies, but the relationship between these Rubies gets a bit complex when cross-compiling. So yeah, let's skip them today. So yeah, so we use Ruby for various code generation tasks during the build process. And that's what base Ruby is for. It handles things like converting Ruby files to C and processing ERB templates. And recently, PathY is also added to the list by Liamar. And mini Ruby, on the other hand, is mainly used for configuring the extension library during the build. So its main role is to run xconf to generate make files for each extension library. So while mini Ruby has its minimum functionality, it has enough feature to run mkmf. So when cross-compiling, since we cannot run mini Ruby compiled for target environment, so base Ruby is used here instead. But yeah, anyway, it's called mini Ruby upcase. So let's go back to the build trace. So now let's look at how we build extension library. So this diagram shows the how extension library are built using recursive make. So when you run make, it first compiles the interpreter core, then it enters a recursive process of the build to build extensions. So First, it configures all extensions by running make with configure xmake. Next, it compiles the extensions using xmake, which in turn runs the make for each extension. Then finally, it links all the compiled objects back to the interpreter. So this is literally a recursive make. So the process starts with the root make file, and eventually it enters the root make file again. So now we understand how the build system works. Let's look at the challenge we face today. So our first challenge is the large number of build variations. So we need to support so many kinds of build variations, and we have to handle different platforms each. And we support both in-tree and out-of-source build, which adds complexity to path handling. And we also need to support both dynamic and static linking in libruby. And the availability of base Ruby can affect the build process. So many build variations itself the many build variation itself is fine, but the problem is that we have to handle them in both configure and make and other several places. So the problems are spread widely in the code base. So the second challenge is what we call make time dynamism. So our build system uses various make features to handle different build configurations, and while these features are powerful, they make the build process hard to debug and understand. So let me show you some example. So here's one example of make time dynamism. So we use this yes/no pattern to conditionally enable and disable targets. So while it's pretty clever, but it makes it hard to track what targets are actually available and when they will run. So this pattern is used throughout our build process, adding layer of complexity. So here's another example. This code handles the generation of a C file, but differently depending on whether we are cross-compiling. But the condition itself is quite complex, but the main problem is there is no clear way to check which path build actually took without running the actual build. So root cause of all of this problem is actually the limited expressivity of configure.ac, I think. So because we cannot express all our build logic in the configure phase, we ended up pushing a lot of complexity into the make phase. And this makes the build process harder to understand and debug. And also, do you remember how we talked about base Ruby earlier? And here is where it became a problem. So even though turbo build should not depend on the base Ruby, they sometimes do when base Ruby is available. So this has caused real issue in the past. And the problem is that we cannot easily verify that a turbo build truly doesn't depend on base Ruby. So we need a way to validate our build plans to catch these issues before they affect users. So finally, let's talk about the build time. So as we saw the data analysis earlier, both configure and make phases are getting slower, and the configure script is essentially one long sequential shell script. So, and these checks could be theoretically be parallelized, but the current auto tools based system makes it difficult. And also the make phase has its own performance issue. So this diagram shows its impact on build time. So those white space in this graph represent idle time, where some cores weren't being used. So see those blue hatched areas. So that's where we could improve by scheduling better. So the problem is that we cannot start building any extension libraries until all of the extension library are configured. So this stage-wise dependency creates a significant bottleneck in our build. So now we have seen the challenges, so let's talk about how we can improve it. So let's start with the complexity issue. So the key idea here is two. So first, we can move the build logic from make and M4 to Ruby. So this allows us express our build logic more clearly in a real programming language, instead of spreading it across configure and make file and so on. So yeah. And for unintended, so basically unintended dependency introduction, the build system should be able to validate the build plan before executing it. And for performance improvement, we need to address both the configure and make phases by integrating feature detection into the build system itself. We can parallelize these checks. And also by moving away from recursive make to a single build graph, we can optimize task scheduling across the entire build. So eliminating those, it will result in eliminating those idle time we saw earlier. So with those goals in mind, I have been working on a new build system. It's still very much in a work in progress, but let me show you what it looks like today and how we address our challenges. So the vision for this new build system has 3 key points. First, we use Ruby to construct the entire build graph, giving us expressivity we need. And second, we make the build system available as a library. And third, despite using Ruby for development, we ensure that the end user will not need to install Ruby to build Ruby. So here is a simple example of what the new build system looks like. The build description is written in Ruby, which makes it easy to understand and modify. And the build description is essentially responsible for constructing the build task graph. And here is a more complex example that shows simplified version of mini Ruby build. So notice how the feature checks are just a regular task in the build graph instead of a sequential shell script. And this means they can be parallelized automatically. So, and we integrate ERB into the build system itself. So we can generate files like config.h based on the feature check within the build system. And let me highlight two key features that addresses our main challenges. First, we convert our Ruby-based build description into a traditional auto tools-like configure script. And this means that end user will not need to Ruby installed at build time. So they will get the same well familiar configure make experience. So you might think this is something CMake and Mason can do, but it's not because their make files are not portable at all, so we cannot distribute to the end users. And second, because the build system is a library, we can analyze the build graph programmatically. So this allows us to check if we have unintended base Ruby dependency before they cause problem. Making it as a library also allows us to easily integrate the CRuby build into other projects like ruby.wasm or yet another single binary packager. So yeah, of course there are still a lot of things to do, but yeah, we need better documentation, Windows support, and way to handle dynamic dependency. But yeah, I believe this approach addresses the fundamental issue we discussed earlier. And as a first step, I'm working on making it capable of building CRuby. So okay, so today I looked at how CRuby build system has evolved over the year and the challenges we face. I showed a new build system that aims to address these issues, but it's still very much a work in progress. So yeah, so I tried my best to structure my explanation, but it might have ended up just dumping my head. So if anything wasn't clear or you have any questions, please feel free to ask me anything. So that's all. Thank you.